medical devices, wearables, large display, and large area display. Here is a Sony or Samsung flexible display, integrated array antenna systems, soft robotic. Here there's a main aircraft with some sensors and electronics on them. So the attributes of flexible electronics is they are lightweight, they could be durable, they are not constrained by the electrical properties of the substrate. So you can put it on an insulating substrate, polymer substrate, whatever you like, papers. They have non-planar form factors, so you can mold it to helmets, mold it to the wings, and so that actually have a lot of application based on that. And they enable low-cost manufacturing. And on the right, I show you, this is for perovskite solar cells. You can see that as the process throughput in terms of area increases, the manufacturing cost drops. So if we want cheap stuff, then we have to make lots of them. So how do you make lots of them? Let's go back to history. Many of you, Dave, I got this idea by going to museum in London. So the Gutenberg press, everybody knows this is why Bibles make Bible widely available. Okay, and here is some a sketch of them making the Bibles, and this is what today what we call sheet-to-sheet manufacturing. They make one sheet, they make another sheet. They have the same mold to print the same pages. So this is making it pretty fast. Now, what do we know that's making things really fast? That's newspaper. So this is roll to roll. You're printing at a speed of 3,000 feet per minute. And you can calculate that. That's 34 miles per hour. And that's damn fast of manufacturing. And one thing you notice is, well, it's printed on paper for newspaper. Paper, one thing is it's cheap. The other thing is it's flexible. You need a carrier that go on these rolls to make it flexible so you can print things on them. So we want to do this for electronics. So and that's what people are working on nowadays. Okay, so I show you this is actually a Eastman Kodak production line. You can, and my collaborators in Energy Materials Corporation are making perovskite solar cell using this method. So there's a roll-to-roll machine. Can you see my cursor here? Or I should bring up something.
We can see the cursor.
Okay, so there's a roll-to-roll machine here. You have different stages to deposit things, and you have then you have to anneal it. Okay, and then you have testing and things. I should mention that the RFID tags that you find everywhere, that's made very cheap by roll-to-roll printing. And EMC is have done the modeling to show that a single manufacturing line like this, and this is a real picture of what this look like, they can produce, I think it was 3 gigawatts of energy produced by the solar panel per year, which translates into 15 cents per watt. And then the capital cost to make these solar cell is 1/10 of the capital cost to make silicon solar cell in terms of manufacturing. In order to do this, they have a 60-foot oven to dry to do the drying and annealing step. So I mentioned that we need flexible substrates. So what kind of flexible substrates we are talking about that we want to make electronics on. So most of these polymers, PET is the most common one, and PEN, and people often use polyimide because polyimide can go to higher temperature, so you can use the regular thermal annealing. Another interesting thing is Corning's willow glass. This is a picture of willow glass. You can actually really bend it. It's 100 micron thick. So the one thing I want to point out is the temperature. PET is the cheapest and it's most widely available. You can't really go above 150 C. Just burn it. Willow glass I mentioned is a glass, so it has very different properties from the other substrates. And so one important property is coefficient of thermal expansion. You look at all the polymers; they are very high, and willow glass, because it's an oxide, is low. So in general, oxides are below 10 and polymers are above 20. So this is a big difference between thermal expansion coefficient. CTEs will cause problem when you heat up by the whole stack of materials. We'll come back to that. Okay, so what about the active material? What do people use? You can use organics or metal oxide. Those are the two things. They can both solution deposit. For metal oxide, for those of you who have worked on it, salt gel chemistry is very well known to make metal oxide. Organics, the pro is because they are more like polymer. Their CTE and mechanical properties are similar to the substrate, so they don't have the CTE mismatch problem. They are solution processable, and most of them you can do this at low temperature. The con is they usually have low mobility, and for special polymers or organics, they could be very expensive. Metal oxide, the pro is you can get high mobility, the high mobility or conductivity materials, and you can get all kinds of different things. Organics are not so good as you got organic you can use for insulator. They're not so good as a conductor, and then very few are ferroelectrics or ferromagnetic, and the very superconductors is way low in temperature and magnetic. So oxide has all these different properties that is a match by organics. And also most oxides are cheap. The bad part about metal oxides is they require high temperature processing. If you do salt gels, you have to heat up to convert it to oxides. So the CTE and mechanical properties, oxides are brittle, so they are very different from the polymer substrate we want to use. So also another issue with metal oxide is we have choices of vacuum deposit or solution deposit. Vacuum deposit, people usually deposit at room temperature or low temperature. They would do regular photolithography, and then they do thermal annealing afterwards, or some people call it activation, to get high performance and to get more crystalline material, higher mobility, so on. Solution processing, we have to deposit as a salt gel precursor. Then you must heat it up to really high temperature, 400 C typically, to form the metal oxide film. Now, you cannot do traditional photolithography before you do this annealing step because the salt gel film can be damaged. And if you take a whole film and then you convert it to oxide, then you want to do photolithography, then you run into the problem with CTE mismatch. So here I show you an example that if you try to convert the whole sample to high temperature, so you heat it up I think in this case, 250 C, okay? The bottom substrate want to expand a lot because their CT is large. Oxide does not want to expand, their CT is low. So the oxide is being stretched and cracked to pieces, okay? So then you cannot get a continuous film that way. Also, you can't go to really high temperature. This I got the website. Your polymer just completely get burned. So those are the challenges for us to make flexible optoelectronic using metal oxide. Okay, so this is the main topic of my talk. So how do we do this? We're going to do annealing without heat. We're going to use photons. And I want to acknowledge my students, Trey Donis, who got his PhD in December, and Wei-Jie Zhu is on the call, and Robert Piper. And also we work with Kurt Schroeder and Novacentric, and this is supported by a DOE grant. So hopefully my co-open have explained to you the challenges we have, how we want to make metal oxide films and maybe other inorganic electronics on flexible plastic substrate. And the challenges, plastic substrate cannot go to high temperature, and CTE mismatch during equilibrium thermal annealing will cause mechanical failure of the oxide film. And then next, we will talk about how do we do this for a large area in an energy efficient way, and how do we do it fast? So how do people lower the temperature? There are two approaches. One is called combustion synthesis. That I'll explain in more details. So basically, this is reaction coordinate. This is your product. Conventional sol gel, you start with this with very stable things. You have a huge energy barrier to get to your final product. But combustion, you add fuel and oxidizer into your precursor. So you start in a more higher level, so you have a lower barrier to go through. So that's one way. Another way is using non-thermal energy. So this includes microwave, light, using laser UV lamp, or reactive oxygen atmosphere. So today I'm going to focus on using light. So on combustion synthesis, so this is a conventional sol gel synthesis, which typically needs to have activation energy above 400 C. On combustion, you add a fuel. Here are some examples of fuel: ACAC, urea, or glycine. And you use an oxidizer, which in our case, we always use nitrate. And you can reduce the temperature down from 400 C to 200 C to make metal oxide. So this is from Tobin Marks' group, showing that the TGA and DTA to show that the red ones are with combustion, the blue ones are regular sol gel. A green one is also combustion using urea, red one using ACAC. You see that the blue one is conventional sol gel. It converts at maybe 350 C. And then with the combustion, you can lower that to 200 C. This one is less clear, but you also see a lower temperature. This one is IZO. You see clear low temperature when you finish the reaction happen at much lower temperature. So this is the one way to, so this is the main channel from chemistry point of view to lower the temperature needed to make metal oxides. However, 200 C, as I show you, is still too high for PET. So and the other thing is, wait, let me just show you this. This is just visual to show you the difference between combustion and non-combustion. So on the left side is a film, so a drop of a precursor without glycine. And so on a hot plate, both of them are 180 C. And you see the left side, pretty much you see the solvent gets boiled and evaporated, and nothing happens. The film just dries. Okay, so that's regular soft gel without combustion. This one with glycine, so you see very quickly, you see those sparks. You see lots of sparks. Those are combustion. So, so obviously when we make our film, we don't put that much glycine there, so we burn our films, right? But this is to show that it can sustain a reaction. The two hot plates are exactly the same temperature, so it has the fuel inside, so it doesn't need much external energy to cause the combustion. So, however, with combustion synthesis, you still needs many minutes, 20 minutes to an hour, and also you need required temperatures still greater than 200 C. So this is a trace paper. So we were trying to make these oxide transistors and capacitors with salt gel. And so what he found is we can simultaneously, by using UV light, in the UV-Ozone cleaner, we can simultaneously pattern the salt gel film and at room temperature, and then you can do an annealing at a small area, so there's no CD problem. So how this works is he spin coated a film, he puts a mask on and exposed to UV ozone, then he brings in developer to get a squared. So the part that's not, so for those of you who do lithography, this works kind of like a negative resist. The part that sees the UV light stays, they cross-link. They don't completely convert to metal oxide yet, but they convert enough that you can remove it in the solvent. So here is optical microscope picture. This is a spin-coated precursor film. This is after UV ozone, after the exposure. And you can see it because, especially on the metal, you can see it because the index and the thickness has changed. And then this is after rinsing off, the part that did not see light got rinsed off. And this one shows you can repeat this and deposit 2 layers. And because Trey was doing this by hand, the alignment is not great. You can see 2 layers. And then you can take these 2 layers and anneal to 200 C or so to convert to metal oxide, and you don't see any cracks. On the right, I show you how we make a full transistor. The blue region, actually the gate dielectric, his aluminum oxide is occupied the whole thing here. And then this is the reddish part is the indium oxide semiconductor. And this is the bottom gate. And this is the source and drain. And here's the channel. So we can make transistor this way on flexible substrates. So you would ask, well, do we know how this works? Why, when we shine UV light on, it stays? So first, we want to confirm. We start with a let's say indium nitrate film. So in the XPS, we put on a big the shadow mask with a hole. So this part, the circular part, got exposed to light. Then we can do XPS. The part that did not see the light, you have a nitrate peak. This at 407 EV is attributed to nitrate. And this part that sees light, that has shown no nitrogen signal, is removed. We can also see this in FTIR. This is the nitrate region. And before UV-Ozone, you see the nitrate peaks. After UV-Ozone, that region is flat. And you can subtract the two and see the difference that the nitrate is removed. The aluminum oxide, I also show you aluminum oxide, which is also show the same result. The difference between our indium oxide and aluminum oxide recipe is the indium oxide has ACAC, so it's a combustion precursor, and aluminum oxide is regular salt gel. So even with regular salt gel, this works. The difference is when we look at the UV vis absorption spectrum for the precursor from film, the indium oxide, the one with ACAC, has a huge absorbance around 300 nanometer, and the one without only have absorption below 240 nanometer. This is from nitrate, people know that, and this is from ACAC. So and I also give you the black sticks, the output from our UV lamp. So the one with ACAC, the combustion formulation, can convert faster, okay? And below I give you the photolysis of nitrates, how nitrate decompose. So the shining UV light let us start the conversion by decomposing the nitrate and leaving behind the metals and the oxygen. I should mention the reason we don't use the combustion chemistry for the dielectric is we find that makes probably a more porous film, because the combustion gas has to come out very quickly, and so the leakage is not as good. So for this semiconductor, we use the combustion, and the dielectric we didn't. The consequence is to make a pattern with the indium oxide, we only need 10 minutes. For the aluminum oxide, we need 40 minutes, okay? So here, just I show you the schematic and the picture before. Here is to show you the transistor behavior. And we got high mobilities. And here is a flexible transistor and a good behavior in the IDVD, okay? So we can make these transistors. However, each layer, so this did the aluminum layer, actually we did 2 layers for the gate dielectric. So that's 80 minutes of UV-Ozone and annealing. And the indium oxide takes 10 minutes, okay? So this is still minutes, a long time of annealing. So that brings me to the next topic. How can we do this for large area, and how do we do it fast? So anybody recognize what these people are doing here? Have to do with Italy. Anyone? No? They're making pizzas. So this is the world's longest pizza. 1.15 miles long. It took 11 hours. I calculate that. That's 2.8 meters per minute. I told you we want to do 10 meters per minute in making devices. So this is slow. They have 5 ovens here. Where's my cursor? They have 5 ovens here. This is pizza, right? So pizza goes in and pizza comes out. So if you think about pizza, you know, putting it in the oven is the longest step, is the slowest step, okay? So that, and if you're doing roll to roll, that limits how fast you can make pizza, okay? It doesn't matter how fast you can put pepperoni on top of pizza or cheese on top. It's limited by how long it stays in the oven. So that is our problem. Our 10 minutes, 40 minutes annealing. So if we want, people want web speed of 30 minutes, 30 meter per minute, if we have to anneal for 20 minutes, that's, and you need an oven, 600 meters long. Guinness Book's longest oven is 100 meter. That's in Bern, Switzerland. And so a 600 meter long oven doesn't exist, okay? So in addition, ovens can incur, if you go to high temperature, there's a large radiative energy loss. And it, well, 600 meter oven is 600 meters long. So it occupies a large physical space. And the other problem is it's equilibrium heating. It's heating the substrate and the film at the same time. So you always have that CTE mismatch problem, and the oxides are going to crack. So what can we do? So I talked about thermal annealing to death now. There's something called rapid thermal annealing using infrared light. They have limited non-equilibrium heating. Substrate can remain at lower temperature. And people have been using this, but still with high CT substrate, the substrate still heats up and it could cause crack. And that takes minutes, not hours or weeks, but minutes. Today, all photonic curing, well, let me start with laser. Most of you know laser, and you can use laser to locally heat something and convert it, okay? But lasers are expensive, and also you put a small spot of laser to do a larger area, you have to scan. So it's a sequential method. Today I'm going to talk about photonic curing. We are using a flash lamp, so it's non-equilibrium heating. There's a big, I'll show you, there's a big temperature difference between the substrate and the film, and we can do this in milliseconds. So this is a picture of photonic curing. It shows SEM of some metal ink. Okay, this is sintering a metal, and you have a flash xenon lamp shining on it, and what come out, basically, the metal nanoparticle melts and sinter together and form a conducting pattern. So the existing application, most of the existing application is making metal conducting patterns on PET substrates. But you can use for UV curing, drying, annealing of amorphous silicon, or even to delaminate polyimide. And here I show you the picture of a roll-to-roll machine, and the lamp is inside here. So you could use this on a roll-to-roll machine. So there are many variables one can control with this flash lamp. This is a xenon flash lamp. You can control the energy it delivers, okay, or the light intensity. We can control how long the pulse is on. We can control number of pulses. We can control how fast you pulse it. So this have to do with whether the sample cool back down before you hit it with the next pulse or not. There are other variables. For example, you can still heat the sample temperature slightly while you shine light on it. You can blow air with the air line to cool it fast. You can process in air or in nitrogen, so you can control the chemistry. And you can put a filter to select the spectrum of light you want to use for this. But most of what we do, we're just going to control these two things. I'll show you an example. We also can do number of pulses. Basically, the pulse energy of radiant exposure, that is the energy delivered by the lamp to the sample per pulse. And then if you have more pulses, that's it will cumulatively deliver more energy. So if you are used to hot plate, the first one is you set it at 200 C, and the number of pulses is you leave it there for 10 minutes versus 20 minutes. So if you leave it longer, it gets heated longer. Okay, so how does this work? You shine light on a film, and the film absorbs the energy, and this can happen very fast in micros. So the simulation I show you below has the light on for 500 microseconds, half a millisecond. So first, if the sample absorbs light, it will heat up, and then light turns off. All that heat will gradually transfer into the substrate. So at the end, they come to thermal equilibrium. So this is the simulation we done by taking into the thermal conductivity and specific heat and optical absorption of the film. You see that the film temperature when light is on shoots up really fast. You turn off the light for the temperature come back down. And notice this could be very high, okay? This is the longer scale. So here we only go to 3 milliseconds. The right graph, we go to 200 milliseconds, okay? Then, and I'm plotting the substrate temperature at the bottom here. So all the heat other than radiated out to the environment is going to transfer to the substrate. And the pulse, the half a millisecond pulse is right here. But you can see that after that pulse ends, the film start cooling down, is losing energy to the air and transfer to the substrate. The substrate start heating up, okay? And at the end, the substrate gets to different temperature. That's because their specific heat and are different, so they reach different temperature. Nonetheless, all of them are well below 100 C. So the substrate does not heat up in this technique. So as I show you, film temperature surface can reach high temperature with minimal substrate heating. And the other important thing is you learn in physics, Arrhenius law. The high temperature allow you to have higher reaction rate. So you don't have to have the light on for that long. You don't. So the total energy delivered to the film can be low, but because you reach a high temperature, you have very fast reaction rate. You can do your phase transformation or during that time without putting in a lot of energy. Okay, so let me show you an example of, we use this to patent zirconium oxide film as a dielectric. So you spin coating, you dry, and here I'm plotting the phase space for processing. The y-axis is radiant exposure in units of joule per centimeter square. That's the energy density delivered by the lamp to the sample. The x-axis is the pulse length of how long that the lamp is on. If we dump too much energy, we will destroy the substrate, okay? Now, if we lower the energy to this blue region, then this is called blanket in this photonic curing. The light deliver the energy, and the whole, so this blue region is supposed to be aluminum. That's the bottom gate. And then you put the zirconium oxide on it. So in this blue region, the whole film turns into zirconium oxide. And you can, if you put a mask on it, then you can put a shadow mask patterning. So in this case, only the part that sees the light would convert enough. So when you develop this part is what's left over. Now, if we lower the energy a little bit, then we get to the regime that we found we can do self-aligned photonic curing. So in this case, I'll explain next in next slide. Only the zirconium oxide on top of the aluminum get converted. So you see here, we're trying to show this, how much of the zirconium oxide got converted is determined on the mask, and you can put a circular mask, whatever shape you want. In this case, the region that got converted is determined by the shape of the bottom metal. So it's only converted on top of the aluminum. If you lower the energy some more, then nothing will get converted. So you zap it and you develop it, everything comes off. So we map these, and let me show you on the self-aligned photonic curing. Oh, where did that go? Okay. So by blanket conversion, this is zirconium oxide everywhere. This is the bottom aluminum contact. So one thing you notice is there are no cracks, and this is because the substrate did not get heated up. This frequency is flat, okay, and then the dissipation is really low. And if we use a shadow mask, I draw for you where the edge of zirconium oxide is. And if you have really good eyes, you can see the bottom edge as well. So this has a shadow mask to put down the zirconium oxide. And the CF is about the same. And this is the self-align, which we only have zirconium oxide around the aluminum. And this is low power, and you get the same CF. And here, because we are making devices, this is 500 microns. So these are big features, and we are using shadow mask. However, I have an undergraduate who have shown that when we pattern the bottom metal down to using photolithography to something small. So I was curious, how small can we do this self-align? And it turns out that it's dictated by how small we can make this metal pattern, and which is, in this case, 5 microns. So this is an interesting way because if you think you are doing row-to-row conversion, then you can't put a mask on and expose to light. You want something that determines where your oxides will cure. And because metals is more light absorbing and there's reflection too than the transparent plastic substrate. So this is PEN that doesn't absorb light. Light just goes through it. The precursor film on top of metal is heated more and selectively. So even though you are at we put in low energy, it can get converted. And while at PEN, it won't. So the other thing you notice is the zirconium oxide is stand a bit past the metal. And so we were looking at what controls that. So that's the overage. So this one, maybe 0.5 micron. So what this James show is there's a nonlinear threshold. When you dump too much energy, then the overage really go up by a lot. So if you use this condition, then you will get a big zirconium oxide pattern. Okay, so this is the, let me skip this. So let me tell you about how we go to 30 minutes per minute. What I show you results is done on this, and it's only go 0.16 meter per minute. That's using the instrument in our lab. Then we went to Novacentrics. They have a bigger system. So here we are dumping 5 joules per centimeter square. So when we go there, we have a system that can dump 14 joules per centimeter square. And with one pulse only. Here we were using 20 pulse. It was one pulse only. And that makes the same kind of quality of film. But now we are 3.2 meter per minute. And then you can use a bigger lamp and same energy, and that would increase it up by a factor 2 to 6.4. And then you can use a bigger power supply, so you can increase the rates that you can deliver the pulse, and that will get you to 52 meter per minute. Okay, so to finish up, I want to talk about Weijie's project, which is making perovskite solar cell. And so we shine the light to convert the perovskite. And here we look at the absorption. And this is the dashed line is the precursor. This is the thermal annealing film. And we use the band gap here, the absorption step at the band gap, to judge how converted our photonic pure film is. So if we give it too little energy, this step is very weak. So that's underconverted. If we give it enough energy, it becomes converted. However, halide perovskite is very fragile. You give it too much energy, then it starts to degrade, and that's the red curve, and we call that overconverted. And so Weijie plot radium energy with pulse lengths. They map out where in the processing space that we can convert, underconvert the film. So let me not go to the detail on why this is. So let me show you that in XRD, you see all these, whether it's short pulse lengths or long pulse lengths, they all get converted. And if you low, medium, high is different amount of energy. So you see that when we increase the energy, the grain size gets bigger, and this is the thermal anneal one. However, at high energy, we see this extra particle. Those are lead iodine, and you can see them in the XRD as well. So the more energy will get you bigger grain size. And we make solar cells. The underconverted one looks like a solar cell, but has very low photocurrent. And this is the proper converted one. And if you are overconverted, the device is shorted. And then we study the parameter of how much energy, and the purple ones are 1 millisecond pulse lengths, and the orange ones are 20 millisecond pulse lengths. So I want to point out that in this space, 20 millisecond, there's a wider range that you can choose the energy versus the 1 millisecond. So and here is plotting VOC, open circuit voltage is this point, JSC is this point, and then fill factor is how square this curve is. So basically, you can see that the current is higher in the middle. The voltage is higher when it's low energy. And the fill factor for the 20 millisecond is higher than the 1 millisecond. So overall, when you time these three together, you have upside down U shape. So in the intermediate energy gives the best result, but the 20 millisecond give better result than 1 millisecond. And if we look at SEM, we see the 20 millisecond film makes a very dense film. 1 millisecond makes these whole films are very porous. That's because at 1 millisecond, we went to much higher temperature to get all the reaction happen in 1 millisecond. So there are gases that's coming out. So it makes a porous film. Okay, and then by this is comparing to thermal annealing. Right now, our current is a little low, but still we get 10% devices, and this the thermal annealing give us 15%. However, the processing time, this is a log scale of processing time. The thermal annealing take 10 minutes, this take 20 milliseconds. So it reduced by 30,000 in terms of processing time. And we also test out the uniformity of this because we use a 6-inch lamp, so we can put sample across the lamp, and we have a 10% uniformity. And we make it on willow glass. And here we are converting the nickel oxide rather than the MAPI, the perovskite. And nickel oxide takes 250 degrees C for 45 minutes. And we were able to do this at 450 microseconds. So this is reduction in time is 10 to the 6 orders of magnitude. So here in conclusion, I show you YJ making the perovskite film. So the spin coating is the same. When you do roll to roll, you would do slot die coating or some large area coating method. And then he's putting into our pulse forge tool. And this is the precursor film. I show you the UV vis, that's very low. And then you see it converted. Whoop. Okay, so that's what you look. Remember, you see he used a magnetic strip to hold it down, so that part didn't see light. It's a precursor color, and the middle is both converted color. So so that's what I show you how we are looking at using photons to do material processing rather than phonons, rather than use heat. And this is my group at UTD. And I also like to thank my collaborators and my funding agencies who support other projects. So, okay.
Well, thank you very, very much, Julia.
Thank you.
Good talk. And we've got some.
Sorry, it's been long.
Some claps happening on the Rogues Gallery over here. So if people have questions, John Conley has a question.
Hey, Julia, very nice presentation. Thank you.
Thank you.
Let's see. I didn't get a good look at slide, I believe 10. I think you talked about some other ways to add energy, and you may have mentioned the source you were using on that page.
10?
Pretty far back.
Type 10 and return. I think that works.
This one?
Maybe it was, let's see. Can I see it again?
This one?
No, it was 10. I think it was 10. Oh yeah, it used non-thermal energy for annealing. So you talk about some other potential sources of energy.
Mm-hmm.
And have you tried microwaves?
No, I have not tried microwaves. We use microwave to make materials, microwave synthesis, instead of using oil baths. So microwave can, but microwave it's not that easy to use.
Okay.
A microwave will work. I mean, so we do nanomaterial synthesis using microwave.
Oh yeah, I've heard of that. So the wavelengths that you're using, I guess you said it's a xenon flash lamp?
Yes, so we use broadband. Everything I show you is broadband.
So
well, not everything. The one in UV-Ozone is using mercury lamp.
Okay,
But
mercury.
the photonic curing is using broadband.
So I guess, is it heating or is it direct UV interaction with the breaking bonds?
I'm writing a proposal. Giving money to study for metals heating, right? Because metals strongly absorb, and but for salt gels, it's very, and so people have you can do photochemical reaction directly versus it can absorb. So I would like to figure out which components and how does that depends on the precursor formulation, and how does so we can design a better process, more efficient process.
Very good. Well, thank you. Hope you get your funding.
Well, maybe I'll put you down as a reviewer.
Johan has a question.
Yes, well, first of all, thank you, of course, for the presentation. It was very interesting and informative. My question related to the actual, the flash lamp, and one of my questions was, you're talking about, sort of doing a lot of this annealing with photons. It's obviously also well understood that photons act as both, somewhat of a particle and a wave, but mostly I was concerned about the wave part. Is there any concern about potentially uneven annealing with the wave fronts produced by your flash lamp?
Are you talking about laterally, or are you talking about in Z direction in the depth?
I like just across the surface, like potentially, if you're mostly focused like on the center of your target, like might the edges potentially get a little less than the center?
Right. So this lamp is 6 inches long. So I quickly went through the uniformity. So the lamp intensity is spec to be uniform, 2% variation across. Okay. So the lamp itself is 6 inches long. This yellow rectangle is the area that's covered by one pulse. So this is macroscopic.
Okay, that makes sense. I wanted to check just to see if there was like any, little bits in there, but thank you.
Julia, I had a question about the modeling that you did to show that the substrate didn't increase in temperature and stayed below 80 K. Have your results shown your modeling to be so good that you almost don't have to do the experiment anymore? Are your models showing anything surprising?
So the modeling is very crude, right? So because the modeling we put in absorption, but not wavelengths dependent absorption. Usually that we just measure it. You have a balloon, you can measure it with the sample, how much energy the matter and then you put the sample on top and you measure it. So you experiment it how energy and look in literature or you can vary for speaking activity, but it's not taken into the initial impedance. So we use it as a guideline to tell us where to start doing an experiment. Like I show you, there's so many, so we kind of see where we can start and do experiment. And we have to know whether machine learning AI would help. And Trey basically tells me that I'm your AI. I look at the film and I decide how to vary it to optimize.
Anybody small enough group now that you can just have a
Yeah, I have two questions. Do you guys run XRD on those films to see if they're crystalline?
They're not. We did XRD that we can't see any crystal. None of our oxide films are crystalline.
So one thing that, with the aluminum, I would expect that to get very hot during these. And that's probably was, I don't know what your precursor chemistry is, but I would think that that's what's driving that chemistry forward. Is that how you guys think of it?
For the self-align, yes. For the self-align, yes.
So the photonic curing, photonic curing is actually more like a anneal that's really specified to a certain area. In this case.
Right. So if you are low enough in energy, the yellow region, yes, it's using the aluminum is helping it to convert. But when it's high enough, it converts the whole thing.
Right. And so with that, I have a question, I guess. I'm not sure if you guys have probed, what the zirconia film looks like on that aluminum pad versus what it looks like on the outside of that pad. Because I would imagine that it would get much hotter on that pad than it does on the outside of the pad.
No, we haven't done that. We've done it for AFM, and AFM doesn't see much, but we no, so I don't know what to study. I don't think there's much difference in XPS.
Okay. I just have one more question on the solar cell.
Mm-hmm.
So it looked like the film when you deposit it is colored, so you're going to get some absorption, and it looked like from the UV-Vis spectrum that it was actually fairly low absorption. But I'm curious, once that chemistry starts, that film turns black, correct? And then
Yes.
you're going to get more absorption. So really, you're doing the chemistry, and then you're kind of sintering. Is that kind of how you guys think about that?
Yeah. So it crystallize it. So the precursor is down here, and so to convert the halide perovskite is much easier than nickel oxide or zirconium oxide because it absorbs light. So even this, it doesn't absorb much, and then you see this green one? So it basically go from the dashed line to the green one and to the blue. So the blue one has gone through the green stages. So in this case, yes, as it converted, it becomes even more light absorbing.
Okay, I think I was confused on this. Was it what is the dashed line? Was that
That's
precursor?
the precursor.
Okay, okay.
That's the light, dirty yellow color.
Yep, okay. Great.
And then the green one and the blue one, by eye, they look, I mean, various shades of brown.
Yeah, great. Thank you so much.
Anybody else? Well, I guess we're already doing what we would do, which is hanging around to chat to the speaker, but certainly let me thank you formally, Julia, for a great talk. Thanks a lot. Learned a great deal.
Thank you for inviting me, and sorry run a bit long. It's like I tell you, this is first time I give this talk.
Well, we're glad to be your guinea pig.
Yeah, thank you for being my guinea pig.
We are indeed. Good. So can you see all the things in the chat? You have many thank yous and
how do I go to the chat?
There should be a chat option at the bottom or along the bar that has got next to the share.
Okay,
perhaps.
I see it now. Okay. Somebody said I have a question.
Oh, I was taking those questions as they were asking.
Okay.
So you answered all of them. I wanted to just ask if you have a moment. I didn't fully appreciate, did those zirconium oxide films, did they not crystallize? Are they amorphous oxides?
They're amorphous oxides. So far, everything we've done with these photonic curing are amorphous oxides. So we haven't tried zinc oxide. One reason we would like to stay with amorphous oxide is if you are on a plastic substrate, you bend it, crystalline oxide is not good, right? They're going to crack along the grain boundary.
Yeah, I wouldn't have thought zirconia would stay amorphous, but it does.
It is.
Well,
or maybe they are nanocrystalline.
Mm-hmm. Yeah, but X-ray amorphous at least.
X-ray, we didn't see anything. I mean, people say we make nickel oxide. People say nickel oxide would be crystalline. People even publish nickel oxide, but actually our thermal anneal, our photonic pure nickel oxide, nothing is crystalline. So maybe you have to do with the precursor.
Yeah. Others? Good.
So Janet, you're a metal oxide expert. So is there anything interesting that come to your mind that we should try?
Well, now that you ask, we've been doing work on amorphous titanium.